everything changes with respect to time. Everything changes. It doesn't matter what we're talking about. dB/dt, bushels per time. Okay, and they're going to relate how one thing changes and compare it to how something else changes. So if I change the radius, if the radius is changing at a particular rate, how fast is the volume changing? And that's what we're going to compare. We're not going to compare how much does the volume change. We want to know how fast it's changing. Okay, if this thing is changing at this particular rate, what's the rate of change for this item? That's what we're talking about with related rates. How does the rate of change of one thing affect the rate of change of another? That's what this whole thing is about. Okay, so the derivatives are a little different, but very similar to implicit differentiation. So volume of a cone, and by the way, AP gives you certain formulas. I give you certain formulas as well, if it's something required. The volume of a cone, if you're required to have the volume of the cone to solve a problem, they will give you the formula for the volume of the cone written in the question. Okay, they expect you to be able to figure out the volume of a box. I don't recall ever seeing the volume of a cylinder given, but I've seen volumes of cones, volumes of spheres, surface area of a sphere, if that's involved in part of the problem. They will give you that formula too. Okay, but it's like a box. Come on, you can't figure out length times width times height. Yeah, that one you're on your own. But if it's a little more complicated like this, no, they give it to you. Okay, they don't expect you to memorize it. I don't expect you to memorize it. Any of you here take the SATs yet? Okay, on the math portion, they have a series of formulas on it, right? Same idea. By the same people, by the way. College Board does the SATs, APs. Okay, so the first one. How is dB/dt related to dH/dt if R is a constant? So if R is a constant, then my variables are volume and height. And what we're talking about here is taking the derivative of the volume of a cone where the radius is a constant and the height and the volume are the things that are changing. So I take the derivative of each side. If I take the derivative of the volume, the derivative of V would be dV/dt. There's no number in front of it. There's nothing else. So it's just plain dV/dt. Equals. And then I have to take the derivative of the other side. Everything but h is a constant. So the derivative of a constant times a variable is that constant times the derivative of that variable. What's the derivative of h? 1 dH/dt, because we're doing it with respect to time. So my answer would be 1/3 pi r squared dH/dt. So the derivative of h is 1 dH/dt, because it's the change in height over a particular period of time. Change in height over change in time. Change in volume over change in time. This represents the rate of change of the volume. This represents the rate of change of the height. So I could use this if radius is kept constant. If the height is changing at 3 meters per second, how fast is the volume of that cone changing? Okay, maybe it's like the water level is dropping or something like that. We'll get to this as we go along. Okay. How is dV/dt related to dR/dt if h is constant? Give that one a shot. Just real quick, give it a shot, see if you can do it. Same idea, only height is the constant. R is my variable. Just see if you can come up with it. Okay, so same idea, taking the derivative of the volume of a cone, only height is constant, the radius is a variable, but so is volume is also a variable. Same thing, what's the derivative of V? dV/dt. equals 1/3 pi r squared h. The 1/3 pi h is a constant. R squared is my variable that I'm taking the derivative of. What's the derivative of r squared? 2r, and I'm going to have to slap a dr dt on the end. So I bring down the 2 in front, so that gives me 2/3 pi r h dr dt. That's if the height is constant. Okay. Now, typically speaking, with a problem like this, and this is a real application. You want to know how fast things are changing. How much time do you have before you have to evacuate if there's a problem? You know, all kinds of issues. Let's say I have a vat filled with canola oil, for lack of a better object to put into the vat. Okay, and I'm draining it out. Okay, if I have my vat as a conical shape, what is the shape of the oil within that vat? It's also conical. It's also a cone, right? Okay, as the level drops, the volume decreases, the height decreases, but also the radius changes at the same time, doesn't it? So all three things are changing at the same time. Rarely does only 2 out of the 3 things change. That does happen. Cylinders, if I have a cylinder, it drops in height. The radius doesn't change in the cylinder, right? But in a cone, both of them would be changing. So realistically, I want to be able to evaluate the volume, the radius, and the height, all 3 changing. How is dv dt related to dr dt and dh dt if neither of the variables is a constant? Well, once again, you take the derivative. Derivative of dv dt, I think or v is dv dt, we got that down. Okay. The derivative of 1/3 pi r squared h when r is my variable. When r is my variable, what is h? Go back to your implicit differentiation. Can we take the derivative of 2 variables at the same time? No, we have to do it once and do it again. We do it once for r, we do it once for h. Just like when we had x and y together in implicit. You did it once for x, you did it once for h. You got 2 derivatives for one function, one for each variable. So I do it for r. Well, we've already done it for r, right? 2/3 pi r h dr dt. And then we have to do it again for h, but we've already done that as well, and we're smart people. Why do something twice when you've already done it? Just copy the problem. The idea of this exercise in the beginning is to show you that we're talking about how things change. And we're relating the rate of change of how fast the volume is changing to how fast the height is changing, or how fast the radius is changing. If I change the radius at a particular rate, the radius is decreasing at 2 centimeters per minute. What's happening to the volume? How fast is it changing? And can you kind of see where this might be important? If I know something is changing, how fast is something else changing accordingly? I need to know how fast it's changing, not what it is at a particular time, but how fast it's changing. Because sometimes the rate is more important than anything else. It's not where it is, it's how fast it's moving. Okay? We know where it is here, we know where it is here, we want to know how fast it's moving. Well, the thing about this is we know it instantaneously. It's not like, well, it's here, oh wait, now it's moving this fast, oh wait, now it's moving this fast. We know right now, we're not taking an average speed, we're taking instantaneous speed. That's what calculus lets us do, instantaneously. If it's doing this now, what's it doing now? Not over a stretch of time. Well, it went from here to here, so that's the changed volume. I want to know what it is right now. I want to know this right now. I want to know what it is right now. That's what we can do. Okay? And all of the problems will relate one thing to another. Now, rarely will we have this situation where you have 3 things being related at once. It can happen. It's extremely rare. We will eliminate a variable along the way before we take the derivatives, what we usually end up doing. Unlike max mins, where we had to get it down to one variable, You don't have to get this down to one variable. You actually just want to get it down to the two variables that you're relating to each other. Okay, so if I'm going to compare volume and radius, I want to eliminate heights from my equation. And I'll show you ways to do that as we're moving along. And it's specific to the situation we're in. Okay? Okay, steps for solving related rate problems. I suggest you get this written down. I'll go over them and then I'll pause so you'll have time to read. Steps for solving related rate problems. 1, understand the problem. Identify what you know and what you are seeking. What do you know? Oh, the radius is this, the volume is this, the height is this is the formula. What am I looking for? Oh, I'm looking for the rate of change of volume, or I'm looking for the rate of change of this. Okay? Develop a mathematical model for the problem. Draw and label a picture. Oh my God, pictures will be so helpful when you're doing these problems. If you're doing the rate of change involving a conical tank, draw a freaking cone and draw it big enough. And oh my God, this is so frustrating when a kid brings a problem up to me and they've got their piece of paper and the drawing is like that big, about the size of a dime. And I'm like going, how can you read any of the labels on that? Draw it big enough that you can put labels on it and see them. And that your teacher who's got bifocals can read them too. I'm old. Don't make the pictures so tiny I can't read the things. You're taking a test, you got room, draw a diagram big enough that you can see what's going on. It's one of my pet peeves. I drew a diagram. Really? It's about the size of a dime. Okay, write an equation relating the variable whose rate of change you seek with the variable whose rate of change you know. You will be given one rate of change and have to find how something else is changing accordingly. For example, from the previous ones, you'll be given the rate of change to the radius. You'll have to find how fast the volume is changing. Okay, so you're going to need an equation that relates volume to radius with no height. We'll eliminate the height if we need to do that. Okay, if the height's constant, then no, we don't have to worry about it. Differentiate both sides of the equation implicitly with respect to time. That's where the dt comes in. Reminds me of a calculus joke. The agony and dx dt. Okay. Substitute values for any quantities that depend on time. Interpret the solution. Plug the numbers in. What do you get? Okay, that's what that comes down to. Plug in the numbers. What do you get? You will be given lots of values. You'll be asked specifically what you're looking for. Okay. Example number 2. A ladder 20 feet long leans against a vertical building. I use plumb. For all those people who know construction, it's plumb, straight up and down. If the bottom of the ladder slides away from the building at a rate of 2 feet per second, how fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? What is the rate of change of the angle between the ladder and the ground? This is huge. Calculus loves to ask sliding ladder problems. Oh, I love the sliding ladder problems because they're easy. What are we dealing with? We're dealing with a right triangle. Right triangles are easy. Okay, trig functions are easy for right triangles. And then what is the biggest, most popular equation that you use with right triangles? Yeah, it's Pythagorean theorem. A squared plus b squared equals c squared. Okay, same thing. And you're going to need those for this problem. Okay, so first thing you want to do is you want to know what's given and what you're looking for. And draw a diagram, label the diagram. So a ladder 20 feet long leans against the vertical building. The bottom of the ladder slides away at a rate of 2 feet per second. Let's give perspective to this. We're going to call this Y. We're going to call this X. We'll call that Z. Okay. So Z is 20, right? 20. The next, so 20 feet long, so that means it's the length of the ladder. If the bottom of the ladder slides away from the building at a rate of 2 feet per second, a rate of 2 feet per second, what is changing? One of those three things is changing with the bottom of the ladder sliding away. X. So that tells me that dx dt, because it's a rate of change, feet per second, second time. X is measured in feet in this particular case. So dx dt, that tells me that dx dt is 2 feet per second. Is it a positive or a negative? Positive. Depends upon your perspective, but in this case, what we're looking at, it's going this way at 2 feet per second. So it's moving in a positive direction. Okay. How fast is the ladder sliding down the building? Sliding down the building, that would be what? dy dt. This would be dy dt. So it's saying dy dt equals what? How fast is it sliding down? What is dy dt? Does that make sense? How fast is it sliding down? What is dy dt? When the top of the ladder is 12 feet above the ground. The top of the ladder is 12 feet above the ground. What dimension is that? Y. So when y is 12, what is, and it's sliding away at 2 feet per second, what is dy dt? Okay. We will need to know what x is. At the instant y is 12, z is 20, what is x? Pythagorean theorem, right? 3, 4, 5 right triangle, multiply 3 and the 5 by 4, you get 12 and 20, so it should be 16, right? But you could also do this. X squared plus 12 squared equals 20 squared. You get 16 for x. Okay. So that means x is 16. Okay. Does that make sense? Yeah. It's 12 feet. The top of the ladder, this top of the ladder is 12 feet above the ground.
I thought it was like
okay. It's that time of year. Christmas vacation. Chevy's on the ladder. They got Chevy's on the ladder. You know, Chevy Chase, Christmas vacation. Putting the lights up, way too many of them. You know, and the ladder's sliding out, and he's sliding down the wall, and he's about to go splat, right? I mean, that doesn't actually happen in the movie, but he has ladder this happen. It's like exactly like this now. Okay. That's why I have a pole to put my lights up without a ladder. Okay. So, I have all the facts I can get, right? I can't get any other information at this time. I know X is changing. I know Y is changing. What about Z? No, is it? I've done it where Z is changing, where Z is an extension ladder collapsing in on itself at the same time, but generally that doesn't happen. So what would you say dz dt is? dz dt would be what? 0. It's a 20-foot long ladder. The ladder does not change length. If the ladder does not change length, there is no rate of change of the length of the ladder. So dz dt would be 0. Okay, does that make sense? Yeah, you have a 20-foot ladder. The ladder's 20 feet. It's a solid 20-foot long. It's not changing length. It can slide away, it can slide down, so Y can change, and Z can change, and X can change, but the length of the ladder is not going to change. So if the ladder does not change length, that means Z doesn't have a rate of change. Its rate of change is 0. Okay? Now, what's our favorite equation for right triangles? Pythagorean theorem. X squared plus Y squared equals Z squared. Take the derivative of the Pythagorean theorem. with respect to time.
Put it there. Put
With respect to time. Take the derivative, because that's our right triangle. That's the equation that describes what's going on. What do I have? I've got a right triangle. I've got one side, I've got two other sides. Take the derivative of that with respect to time. Just like we did on our first step. Just like we did on the first example. The first thing we did. The first example we did. Same idea. You're taking the derivative with respect to time. They're not constant. Technically Z is, but we'll deal with that in a second. What is the derivative of x squared?
2x.
2x dx dt. 2x dx dt, which I'm not in right now. What's the derivative of y squared? 2y dy dt. Let's go. Equals the derivative of z squared is 2z dz dt. Now, I have our derivative. Well, we're taking the derivative of everything with respect to time. Time is the thing that's changing along with those objects. Okay, now, z is constant. I can treat z as a variable or I can treat it as a constant. At this point, I can make that distinction. I could have done it when I took the derivative, or I can do it now. Because what is dz dt? 0. If I put in 0 for dc dt, what happens here? This goes away. And now, if I divide everything by 2, I get x dx dt plus y dy dt equals nada. What am I looking for? What am I looking for? dy dt. How fast is the ladder sliding down the wall? I'm looking for dy dt. What do I know? I know x, I know y, I know dx dt. I have 4 things, I know 3 of them. Can I find the 4th one? Yeah, that's algebra 1. Plug in the numbers and solve for dy dt. That's it. Seriously, it's algebra 1. Plug in the numbers, solve for it. Watch your negatives and positives. And please, 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 leave them in fraction form. Unless it makes no sense to leave them in fraction. And it should be negative, should it not? Yes, it needs to be negative. Okay, are we done with the question?
No.
Oh my God. Oh my God, it asked for another thing. What is the rate of change between the angle of the ladder and the ground? What is d theta dt? Yes, sir. It's negative 8/3 feet per second. Okay. So we need to come up with an equation that relates the angle to the sides. Now, whenever possible, you want to use given information, not found information. Whenever possible, you want to use given information, not found information, and you want to use easy information, not hard information. I would like to avoid using -8/3. It's the only fraction we have. We don't want to use fractions if we don't have fractions. Okay? So, how can I relate theta to two of the sides? Yeah, trig functions. Now, it's really cool because z is a constant. Z is a constant value. Z does not change. So if I can find something relating x and z and theta, come up with a trig function that relates those, that's what I want to use. What's going to relate theta and the hypotenuse and the adjacent side? Cosine. Right? Sine, cosine, tangent. Those are the ones we're going to deal with. The cosine of theta is equal to x over z. You could, but you'd use y instead, and you may have to use -8/3. Do you really want to use -8/3? No. And you could use tangent too. You could use any one of them. I'm using the ones that use the easiest numbers to work with. And the ones that will give me the easiest derivative as well. Because if I use the tangent, then I have to do dx dt and dy dt. Here, z is a constant. So when I take the derivative of this side here, it is strictly dx dt. Now, the derivative of the cosine is what? Negative sine theta. Negative sine theta d theta dt equals the derivative of x over z. What? Z is a constant. No, I'm not taking the derivative of the denominator.
No, b plus x.
No, I'm not going to start. Is this not true? What is the derivative of a constant times x? Is that constant? Dx dt. Now I could plug in 20. I could plug in 20 for z at any point I want to, because it doesn't change. If I know it's a constant value, I can plug in that value at any time. I can plug it in here. I can plug it in here. I could have gone back to here and I could have put 20 in there. I could have put 20 in there, and it would have been fine at any point, because it is a constant period all the time. Its known value does not change. So I couldn't plug it in at any time I want. Now, start plugging in values. We know what dx dt is. We know what 1 over z is. So this is equal to 1 over 20 times 2. And then the other side, we're looking for d theta dt. And then we have the minus sine of theta. What is the sine of theta? Well, sine is what in a right triangle? Opposite over hypotenuse. So the sine of theta is what? 12 over 20, which reduces down to 3/5. Negative 3/5. Because the sine of theta is negative 3/5. Because we have a triangle specifically we're working with, so we know what sine of theta is. Solve for d theta dt. Negative. Okay, 1/10 times 3/5 is negative 1/6.
Sure.
What would the units be? What would the units be? I think radians. It used to be measured in radians. Measured in radians, I think is what it would be. Kind of hard to tell. That's a tough one. I would go with radians on this one. Oh, you're just agreeing with me to make me feel better, aren't you? Well, there are a few things that I have to stop and think, and I get confused. This is one that always gets me: is radians or degrees? I'll leave the units off and just go with the number. Okay. Which is okay as long as they don't ask specifically for units. If they ask specifically for units and you leave units off, you lose points on the AP test. Because if they ask for units, they want units, and they make it worth something.
Is it common that they ask for units, or
They will state specifically, including units, with the correct units or something like that. You will see questions. Okay.
Oh boy.
Okay. Yeah. Take a minute. Write it down. Thank you. Okay. So, as I was saying, so we have dVdt is 10 cubic feet per minute. It doesn't say dVdt. It says the water's being pumped into the tank at cubic feet per minute. You people have been around long enough and done enough things that you should recognize that cubic feet is a measure of volume. And per minute, it means, volume over time. dVdt. Okay, you should be able to figure out that volume is represented. And if it's volume over time, that's a rate. dVdt, change in volume over time. Approximate the rate of change of the water level. That's what? Water level. That's measuring what? Height. So it's saying, what is dH dt? At the instant the water level is 3 feet deep. When H is 3, what is dH dt? At that instant. It's that instantaneous change. It's not over change. It's what's happening right now. What is dH dt right now? So, what variables am I dealing with? Volume and height. Those are the two things that I have any information about. Volume and height. The problem is we have a cone which also has radius. And the radius is not constant. If it was a cylinder, we'd be good because the radius is constant in the cylinder. This is a cone. The radius changes. We don't know dr dt. We don't know r. So somehow we have to change this equation in terms of h only. We need to eliminate r from the equation. It's not that hard to do. What kind of triangles are those?
Right, triangle.
There's a relationship between the two other than right triangles. What is that relationship between them? They are similar triangles, which means that they are proportional, which means the radius over height is always a constant ratio. So that means r over h is equal to 6 over 12 all the time. So this reduces to 1/2, right? So r equals 1/2 h. The radius is always half the height. Or we could also say the height is always twice the radius if we needed to substitute and for H, but we want to solve for R. So we want to replace R. Okay. For purposes of working the problem, it's better to write it as H over 2. Okay? Algebraically, H over 2 is a lot easier to work with. So, take H over 2, put it in the volume of a cone, put it in for R. Replace R with H over 2. Simplify. Do that now. Remember, most of calculus is algebra. Simplify. Because H over 2 squared is H squared over 4. 4 times 3 gives me my 112. And then H squared times H gives me H cubed. Now I have volume related to height. Now what? Take the derivative. dV dt equals, bring down the 3 over 12 becomes 1/4 pi h squared dh dt. What are we looking for? dH dt, what do we know?
H is 3.
H and dV dt. You have 3 things in there, you know 2 of them, find the third. I mean, how hard is that? You have 3 things in there that you know 2 of them. Put numerical values in for the 2 you know, find the third you don't. And the water level is being pumped into, so it is positive. Sorry. This is one where converting it over to a decimal would probably be a good idea, just to give you a better idea of how many feet per second. Okay, 40 over 9 pi feet per second doesn't really work all that well when you're trying to explain to the engineer that how long they have. Right? Although the engineer would probably be doing this, he'd probably be telling the shop foreman. We will continue.